300 million meters per second, about 186,000 miles per second, 299,792,458 meters per second, if you want to get fancy about it. C, the cosmic speed limit, the number Einstein built his whole theory around. You've heard this, you know this, except, and here's the thing I want to spend some time on today, do you actually know what you mean when you say that? Because I've been thinking about light for a long time, and the more carefully I look at it, the more I realize that the phrase, the speed of light, is doing a tremendous amount of hiding. It is concealing something that is so weird, so counterintuitive, and so absolutely fascinating that most people, even people who work in physics, don't really sit with it long enough to feel just how strange it is. So let's slow down, no pun intended. Let's start from something you can actually picture. You're standing outside on a clear night. You look up at a star. The light from that star and those photons, those little packets of electromagnetic energy, they've been traveling for maybe hundreds of years. They left that star before anyone alive today was born. They crossed the vacuum of space, this enormous, empty, cold nothing, and they landed right in your eye. And the whole way from that star to your eyeball, those photons were moving at c, at 299,792 and 458 meters per second, constant, unwavering, no speeding up, no slowing down. Now here's the first strange thing I want you to think about. Why that speed? Why not twice that speed? Why not half? What decides it? Well, here's the honest answer. We don't entirely know why the universe chose that number, but we do know this, that speed c is not fundamentally the speed of light. I mean, it is, but that's not what makes it special. What makes c special is that it is the speed at which anything massless travels through empty space. It's the speed of causality. It's the rate at which a disturbance in a field, any field, propagates through empty space-time. Light happens to be massless. That's why light travels at c. But if we tomorrow discovered some other massless particle as something with no rest mass at all, it would also travel at exactly c, not because of anything special about light, but because that's what the universe does with massless things. So already right there, the phrase speed of light is a little misleading. It's more like the speed of nothingness, the speed at which the universe can transmit information. Light is just the messenger we happen to see every day. All right, now here's where it starts getting really interesting, because you've heard that the speed of light is constant, right? It's always c. That's the whole point. Einstein said it, the universe agreed, everyone went home happy. But wait, you've also probably heard, maybe in a different class, maybe in a different video, that light slows down when it goes through glass or through water. When you put a straw in a glass of water and it looks bent, that's because light is changing speed at the boundary between air and water, and that bending, that refraction, is the result. So which is it? Does light always travel at c, or doesn't it? And this is where most textbooks just sort of wave their hands and say, well, the effective speed changes, and then they move on. But I don't want to do that. I want to actually dig into this, because the real answer is one of the most beautiful things in all of physics. Here's what's actually happening when light passes through glass. Now, glass is made of atoms. Those atoms contain electrons. And when a photon, a little packet of light, comes flying in from outside, those electrons respond to it. The electric field of the incoming light wave shakes those electrons. It jiggles them. And a jiggling charge radiates. It produces its own electromagnetic field. So now you've got the original light wave moving through, and you've got all these electrons in the glass vibrating and producing their own radiation. And those two things, the original wave and the new radiation from all those jiggling electrons, they add together. They interfere. And the result of that interference is a wave that, when you measure how fast the peaks and troughs are moving through the material, appears to be going slower than c. But here's the thing, and this is the part that stops most people in their tracks when they first hear it. The photons themselves, the individual photons, they're still traveling at c. They haven't slowed down, not one bit. Each individual photon is still moving at 299,792,458 meters per second, just like it always was. What's happening is something much more subtle. The light is being absorbed by electrons and then re-emitted, absorbed and re-emitted, over and over again. And each time there's a tiny delay, just an incredibly tiny, vanishingly small delay between absorption and re-emission. And those tiny delays add up. So the average speed at which the light moves through the material, the rate at which the wave front progresses, is slower than c. But no individual photon ever traveled slower than c. Isn't that remarkable? The light doesn't slow down. The light just keeps getting interrupted. It's like trying to walk across a city when you keep running into friends who want to chat. You're always walking at the same pace between conversations, but your average speed across the city is slower because of all the stopping. Now, I want to stay with this glass business a little longer because it introduces something even stranger. You know that light bends when it goes from air into glass, right? Refraction. Snell's law. You've seen it. The angle changes, but why does it bend? Why doesn't it just go straight through? The usual answer is because it slows down. And that's not wrong exactly, but it's incomplete. The real answer, the answer that actually satisfies me, is about something called the principle of least time, or sometimes Fermat's principle. Here's the idea. A photon going from point A to point B doesn't just take one path. In quantum mechanics, and this is Feynman's own beautiful way of thinking about it, a photon takes all possible paths simultaneously. Every single path between A and B, the straight one, the curved ones, the zigzag ones, ones that loop around the other side of the galaxy. Every path, but the paths don't all contribute equally. For most of the crazy paths, nearby alternatives cancel them out through interference. They destroy each other. The only paths that survive, and the ones that add up constructively instead of destructively, are the ones near the path of least time, the path that takes the shortest time to complete. So when light goes from air into glass, it bends because the path of least time is a bent path, because part of the journey is in air, where the light moves fast, and part is in glass, where it moves slower. And bending at just the right angle allows the photon to make the whole trip as quickly as possible. It's like a lifeguard running to save a drowning swimmer. You run on the beach at full speed, but when you hit the water, you angle in, and because swimming is slower, and the fastest total path is not a straight line. Nature, it turns out, is extremely economical. It finds the fastest route automatically, not because light thinks about it, but because of interference. The slow paths cancel themselves away. Only the fast path remains. This is Feynman's path integral formulation of quantum mechanics, and it is, in my opinion, one of the most astonishing ideas in the history of human thought. Okay, let's go back to C, to this cosmic speed limit. Here's something that should bother you, if it doesn't already. Light in a vacuum always travels at exactly c. Every observer, no matter how fast they're moving, measures the speed of light as exactly c. You could be racing toward a flashlight at 99% the speed of light, and the light from that flashlight would still come at you at c. Not c plus your speed, just c. This is the central weirdness that Einstein built special relativity on top of. And most people hear this and say, oh, okay, Einstein, sure, and they nod. But do they feel how strange it is? If you throw a ball at me and I'm running toward you, the ball hits me faster than if I'm standing still. Everything works that way, except light. Light doesn't care how fast you're moving. It always comes at you at c. The reason, and this is the deep reason, is that c is not actually a property of light. It's a property of space-time itself. It's baked into the geometry of the universe. The universe has a structure such that there is a maximum rate of information transfer, and that rate is c. Light travels at that rate because it's massless and there's nothing to slow it down. But c would be c even in a universe with no light at all. In fact, you can derive c without ever mentioning light. Maxwell did it in the 1860s. He wrote down his equations for electricity and magnetism. And when he found the wave solutions, the solutions that describe electromagnetic waves propagating through space, the speed came out automatically from the electric constant and the magnetic constant of empty space. He didn't put the speed of light in. It fell out of the math. And the number he got was the number everyone had already measured for light. He realized that light was an electromagnetic wave, and its speed was a fundamental property of the electromagnetic field itself. So c is a property of space, of the vacuum, of the fields that live in the vacuum. Light happens to travel at c because it's the right kind of thing. Massless, no resistance from the vacuum, but c is deeper than light. Now here's another thing I want to address, because it comes up and it sounds crazy at first. Can things travel faster than light? Well, the particles of light, photons, travel at exactly c. Particles with mass can get arbitrarily close to c, but never reach it. It would take infinite energy to actually get a massive particle to c. So in that sense, no. But here's what's interesting. The phase velocity of a wave, the speed at which the peaks and troughs move, can exceed c. In certain exotic materials, the phase velocity of light can actually be greater than c. That sounds alarming. Doesn't it violate Einstein? No. And here's why. You can't send information using just phase velocity. You can't encode a message in the peaks and troughs of an infinite wave. To send a signal, you need a pulse, a wave packet, an envelope. And the velocity of that envelope, the group velocity, then that's the one that carries information, and that cannot exceed c. In fact, in those exotic materials where the phase velocity exceeds c, the group velocity on the actual signal moves slower. The two are different things, and only the group velocity matters for causality. Only the group velocity tells you how fast information travels, and information never exceeds c. There's also something called quantum entanglement, which some people claim means information can travel faster than light. It can't. Entanglement correlates the outcomes of measurements at two locations, but you can't use it to send a message. When you measure your entangled particle, you get a random result. And when your friend measures theirs far away, they also get a random result. Those results are correlated. But you can't control your result, so you can't encode anything into it. No information travels. The universe is very careful about this. Let me tell you something that I think is genuinely underappreciated. The fact that we even have a concept called the speed of light that stays constant, that all observers agree on, is not just a physics fact. It's a deep philosophical statement about the nature of reality. See, in ordinary Newtonian mechanics, there's no universal speed. Velocities are always relative. If I'm moving at 10 meters per second and you're moving at 5 meters per second in the same direction, you see me moving at 5 meters per second. Everything adds. Everything subtracts. There's no anchor, but c is an anchor. It's the one speed that everyone agrees on, always. It's the same for every observer in every reference frame. And because of that, it tells us something deep about how space and time are knit together. It tells us that space and time are not separate, independent things. They're part of a single fabric, space-time. And c is the conversion factor between space and time. It's what connects them. This is why Einstein's famous equation has c in it, E equals mc squared. The c squared there isn't saying anything directly about light. It's saying something about the relationship between mass and energy, mediated by the fundamental constant of space-time. It's saying that mass and energy are the same thing, just measured in different units, and the conversion factor is c squared. Light just happens to use that conversion factor too, because light is an electromagnetic wave, and electromagnetic waves propagate at the fundamental speed of space-time itself. Here's something I want to leave you with, something that I think is one of the most humbling and beautiful things about this whole subject. We said that photons, individual photons, travel at c in vacuum, and because of special relativity, we know what happens to a clock that moves at c. Time stops. For a photon, if it could experience time, which is a strange notion, there is no passage of time at all. From the moment a photon is emitted from a star 1,000 light years away to the moment it hits your eye, as far as the photon is concerned, no time passes. None. Zero. The photon doesn't experience a journey. It doesn't cross space. In a sense, the photon exists simultaneously at its source and at its destination. The 1,000 years that you waited, that's something you experience. The atoms in your eye experience it. The universe around the photon's path experiences it. But the photon, it connects two events instantaneously from its own perspective. Or rather, the very concept of perspective breaks down for something moving at c. And yet, from our perspective, on our side of the observation, that photon takes exactly as long as you'd expect. 1,000 years for 1,000 light years. Every calculation checks out. Every measurement agrees. The universe is perfectly self-consistent. But that self-consistency is concealing this extraordinary thing, that light, the thing that carries information for us, the thing we use to see the universe, the thing that defines the limit of causality. Light has no experience of traveling. It doesn't go anywhere in its own frame. Distance is zero. Time is zero. It is simply present. So what's the point of all this? What do I want you to take away? I want you to be suspicious of simple answers. I want you to look at the phrase, the speed of light is 300,000 kilometers per second, and recognize that those 12 words are sitting on top of an ocean of extraordinary physics. That c is not really the speed of light. It's the speed of the universe's causal structure. That light in glass doesn't actually slow down. Photons are still moving at c, but interference and absorption and re-emission create the appearance of slower propagation. That the reason light bends at a surface is because the universe automatically finds the path of least time through a mechanism of quantum interference That is one of the most elegant ideas physics has ever produced. That you can't send information faster than c, not because of some arbitrary rule, but because c is sewn into the fabric of space-time itself. And most of all, I want you to feel the strangeness, because physics is not a list of facts to memorize. Physics is a confrontation with the actual nature of reality. And reality, I promise you, is far stranger and far more magnificent than anything we could have made up. The universe doesn't explain itself to us. It just sits there, being extraordinary, waiting for someone curious enough to ask the right questions. I hope you're one of those people. I think you are. Otherwise, what are you doing here?